When I was young, kids would tell their parents that they would do their homework together, while in reality they would end up in places like these to play video games. And from today's perspective, these games look quite simple, but there's actually a lot of computations going on in the background. Today we're going to have a look at old school video games and the mathematics that relate to it, from matrix multiplications to base changes and how we learn to navigate a spaceship. In 1979, Asteroids made a splash. In this little game, you're steering a spaceship that is shooting at, well, you guessed it, asteroids. And one of the difficulties is that in the beginning, the asteroids are quite big, but every time you shoot at them, they start to decrease in size until ultimately they evaporate into dust. An additional challenge are the controls. You have one button that rotates the ship counterclockwise, and the other button rotates it clockwise. You can shoot and you have a boost that propels the ships into space. As you can see, the game is quite difficult. Fortunately, today we're not going to talk about how to steer the spaceship, but actually how to draw it on the screen. The underlying principle is called vector-based graphics. All the shapes and objects on the screen are made up of vertices that are connected by line segments. And if you were to record this screen in slow motion, you would actually see them appear one by one. Interestingly, it might surprise you that the original definition of the shapes is not directly on the screen, but the spaceship is defined with vertices around the origin. Only during gameplay, it is moved, translated and rotated into the right spot. Let's see how that's done. How to rotate the spaceship. A rotation over some angle theta around the origin is a multiplication with the following matrix. Why is this matrix a rotation? Let's start with the unit vectors along the x and the y-axis. The first unit vector with entries 1, 0 multiplied with this matrix results in the first column, cosine theta, sine theta. It is pointing in the right direction, the x-axis rotated by an angle theta. Similarly, the vector 0, 1 results in minus sine theta and cosine theta, again, the expected direction. The vertex of our spaceship can be described as a combination of the two unit vectors. For example, 2 steps along the x-axis and 1 step along the y-axis. After rotation, the location of this point is now 2 steps along the rotated x-axis and 1 step along the rotated y-axis. The coordinates are the same, only the basis representing the points has changed. For the rotation of our spaceship, the controls then increment or decrement the angle theta. For each image, we construct a matrix and multiply it with all the spaceship vertices to obtain a rotated version. Now we can translate it to the right location on the screen. Vector graphics are simple, but let's see how to enhance the appearance. A newer version of Asteroids, Blasteroids, relies on pixel art, which is currently making a comeback in many indie titles. Suppose we have a spaceship image, now on the left, made up of pixels, and we want to draw a rotated version on the right, which represents the screen displaying the game. A straightforward idea would be to apply the same principle as before. We take each pixel center of the spaceship, transform it using the rotation matrix, and the color of the screen pixel changes whose center is closest to the transformed spaceship pixel. Unfortunately, the result doesn't look good. The problem is that you can have several spaceship pixels ending up contributing to the same screen pixel. Further, even neighboring spaceship pixels might land in non-neighboring screen pixels, which can lead to gaps. This issue is known as aliasing. The solution to address this issue is to turn the problem around. The idea will be to start on a screen pixel and discover which pixels of the spaceship should contribute to determine its color. We will assume that the rotated spaceship is drawn at the screen center, which acts as an origin, and use 2 unit vectors along the pixel raster to describe the screen pixel as coordinates. Using this coordinate representation, we can now apply the inverse rotation to see which location on the spaceship would correspond to this screen pixel. In other words, it provides us with a location P on the spaceship from where we need to derive the colors that we want to use. But how to determine this color? Well, the simplest way is called nearest neighbor sampling, where you take the color of the pixel closest to the location P. Here the color is simply red. For a different screen pixel, the process stays the same. Compute its coordinates, transform it with the inverse rotation, grab the color value. Let's apply this process for all screen pixels. Any pixel center inside the spaceship retrieves the color, and the result is a rotated spaceship. While not perfect, at least it looks better than before because we have filled all gaps. Still, as the spaceship pixels are never mixed on the screen, the result looks quite rough on the edges. Hence, we did not resolve the aliasing problem that we mentioned before. Let's try to improve the results by mixing colors. We again start with a screen pixel as before and determine its corresponding location P in the spaceship image. Around P there are several pixel centers of the spaceship, and specifically we will focus on all 4 pixels whose centers are closest to P. These 4 pixel colors will be mixed to determine the final color that we will use on the screen for P. The simplest approach would be to average these colors, which is equivalent to saying that we multiply each color by 1/4 before summing them up. This can be seen as taking an equal chunk of every color and mixing them together. Doing this for every pixel, the result looks like this. At least the rough edges are less visible, but the overall image appears quite blurry. We can do better. Another approach to mix pixels is bilinear interpolation. Instead of using 1/4 for each pixel, we determine distinct weights that altogether sum up to 1. The value of each weight will depend on the position of P. Imagine a box around the surrounding pixel centers. We will express the point P in a basis of a vector space whose origin is at the lower left pixel center, shown as 0, 0, and spanned by 2 unit vectors u and v. Their sum results in the position 1, 1, which is the upper right pixel center. Expressing P as a linear combination of u and v yields coordinates alpha and beta, which we will then use to derive the bilinear interpolation weights. Specifically, we are going to consider the relative area of the rectangle opposite to each pixel center. The larger it is, the more impact its pixel's color will have on the result. Observe that if P is closer to a pixel center, the area increases until it covers the entire region between the pixel centers. Calculating the area of these rectangles is actually very easy. Realize that P has coordinates alpha and beta, which corresponds directly to the width and the height of the red rectangle. Hence the weight for C1 is given by alpha times beta. Similarly, C2 is simply 1 minus alpha times beta, and so forth. Bilinear interpolation corresponds to this resulting formula. See how in this case the proximity of P to the red pixel center shifts the resulting color significantly towards red, while not ignoring the contributions of the other nearby spaceship pixels. Similarly, when P is closer to the blue pixel, the result appears more blue. This observation holds for all other locations. Notice that the location on the edge of our region, which corresponds to P lying on the center line between 2 pixels, only 2 pixels, namely these 2, will contribute to the final result. Finally, if P lies on the center of a pixel, then only this single pixel is contributing to the screen pixel's output. Now let's see what happens if we apply this technique to the screen pixels to obtain our rotated spaceship. This time, it doesn't seem too blurry, while also not showing the same rough edges that we initially observed. Here's a direct comparison between the different solutions, showing the clear quality improvement that we have obtained. Now that we went through the details of bilinear interpolation, let's move ahead with an exercise. Today we've taken a look at early video games, and while it seems outdated, much of the technology still applies today. Our 3D objects are now made up of triangles that are also defined by vertices that are connected to each other. The so-defined 3D objects are typically enriched by textures. These are images that are attached to the surfaces. Their pixels are mapped pretty much in the same way as what we've seen today. In today's lecture, we took a look at the inner workings of computer graphics applications, which are of high importance to many domains.
like scientific and medical visualization, architecture and design, movie productions, the interface of your cell phone, and of course, video games. Here at TU Delft you will learn much more about the technologies that shape our world. And there are many surprises for you in store. After all, who would have thought that your homework actually relates to video games? With this, I wish you the best for the future and see you in class.